In this lesson, we will study polynomial congruences. We'll begin our discussion with polynomial congruences mod p, where p is a prime number. Recall that if you have a linear congruence like ax congruent to c mod m, then this congruence is solvable exactly when the greatest common divisor of a and m divides c. So this is solvable if and only if d divides c, where d is the greatest common divisor of a and m. We also saw that when the greatest common divisor, if the greatest common divisor is d, then there's exactly d mutually incongruent solutions to this linear congruence. If the greatest common divisor is 1, we saw that there's a unique solution. So further, if a and m are relatively prime, so if the greatest common divisor of a and m is 1, then there's a unique solution and the unique solution is the inverse of a times c mod m. So after studying linear congruences, it's natural to examine polynomial congruences where the degree is higher than 1. So now we will examine polynomial congruences of the form f of x congruent to 0 mod m, where f is a polynomial, so f of x equals an integer times x to the n plus an integer times x to the n minus 1, all the way down to a1x plus a1x plus an integer times x plus a constant term a0. Where so f of x equals as a polynomial of degree n, so in particular the leading coefficient an does not equal 0, and all of the a's are integers. So and ai is an integer for all I. So we're going to look at polynomial congruences where all of the coefficients are integers. So what do we know about polynomial equations? Well, we know that the degree of a polynomial equation determines how many solutions there are. The fundamental theorem of algebra states that if you have a polynomial of degree n, then the polynomial equation of degree n has n solutions, but the solutions can be complex numbers. So the fundamental theorem of algebra states that if f of x is a polynomial of degree n, and the degree is greater than or equal to 1, then the equation f of x equals 0 has n solutions among the complex numbers. So does the fundamental theorem apply to polynomial congruences? So if you had a polynomial congruence of degree n, would there be n solutions? Well, not exactly. Here's an example. There's actually no direct analog of this theorem for polynomial congruences. So this does not apply to congruences. For example, the polynomial congruence x squared congruent to 1 mod 8 actually has 4 solutions, even though this is only degree 2 polynomial congruence. So if you look at the residue classes 1, 3, 5, and 7, they will all satisfy this congruence. However, when the modulus is prime, we do have the following theorem of Lagrange that we use in our proof that every prime number has a primitive root. So we'll present Lagrange's theorem next. So let P be a prime number. Okay, so if we have a polynomial function so f of x is a polynomial of degree n, with integer coefficients, such that a of n is not congruent to 0 mod p. So in other words, p does not divide an. Then the polynomial congruence f of x congruent to 0 mod p, which is prime, has at most n mutually incongruent solutions. Mod p. So if you recall, I actually used Lagrange's theorem in the proof that every prime number has a primitive root mod m, and I said we'd prove this theorem later. So we're going to prove this theorem now, and the proof is by induction. This will be a proof by induction on the degree n. So what if I had a polynomial of degree 0? So if the degree was 0, then f is just a constant function. F of x will just equal a0. And we're assuming that a0 would not be 0 mod p. So since a0 is not congruent to 0 mod p, there are no solutions to this congruence. So this step is a little too easy. We've even solved the next case if the degree was 1 explicitly. So we know that if n equals 1, if the degree is 1, then we have a linear polynomial for f of x. So f of x equals a1x plus a0. And as I mentioned a few minutes ago, we have shown that the congruence a1x congruent to negative a0 mod p has exactly one solution, mod p, because if a1 is not congruent to 0 mod p, then a1 must be relatively prime to p. So the GCD of a1 and p is 1. So we know that there is exactly one solution to this congruence. So the theorem holds for n equals 0 and for n equals 1. So that's the basis step for induction. So now our inductive hypothesis. Suppose the theorem is true for all polynomials of degree k, where k is an integer greater than or equal to 1. So we want to show that the theorem is true for polynomials of degree k plus 1. So let's assume we have a polynomial of degree k plus 1 with integer coefficients. So let f of x be a polynomial of degree k plus 1 with integer coefficients and whose leading coefficient is not divisible by p. Okay, so we want to show that the polynomial congruence f of x congruent to 0 mod p has at most k plus 1 mutually incongruent solutions. Well, if the congruence f of x congruent to 0 mod p has no solutions, then that would be less than k plus 1, so the theorem would be true. Okay, so if the polynomial congruence f of x equals 0 has at least one solution, let's call it C. Okay, so this congruence has a solution C, then f of C is congruent to 0 mod P, and we can write f of x congruent to the linear factor x minus c times a new polynomial g of x mod p, where g of x has degree k and the same leading coefficient as f of x. So if C is a solution to this congruence, f of x equals 0, congruent to 0 mod p, then I can factor out the linear term x minus c from f of x, and notice that the leading term of x minus c is just 1, so when I combine it with the polynomial g of x, I should still get the same leading coefficient of f of x. So g of x has the same leading coefficient as f of x. Now the inductive hypothesis comes into play. Since p is prime, f of x, which is congruent to x minus c times g of x, congruent to 0 mod p. This implies that x minus c is congruent to 0 mod p, or g of x is congruent to 0 mod p. So we know that if a prime divides a product, then the prime will divide one of the two factors. So if x minus c times g of x is congruent to 0 mod p, that implies, this is Euclid's lemma, that x minus c is congruent to 0 or g of x is congruent to 0 mod p. So one solution to f of x congruent to 0 mod p is c, and then the other solutions come from the congruence g of x congruent to 0 mod p. But since g of x has degree k, by the inductive hypothesis, we're assuming that there's at most k solutions to this congruence, g of x congruent to 0 mod p, and since we only have one other possible solution, x congruent to c, that gives us a total of at most k plus 1 solutions to the original congruence. So that's how the theorem is finished. So let's just write up all those details. Then we have x congruent to c mod p, or x is a solution of the congruence g of x congruent to 0 mod p. But this congruence has at most k mutually incongruent solutions. but g of x congruent to 0 mod p has at most k mutually incongruent solutions by the inductive hypothesis. Therefore, the congruence f of x congruent to 0 mod p has at most k plus 1 mutually incongruent solutions. So if f is a polynomial of degree k plus 1, we've shown that f of x congruent to 0 mod p has at most k plus 1 mutually incongruent solutions. Therefore, we can conclude by the principle of mathematical induction, the theorem is true for all degrees n. So Lagrange's theorem tells us that if we have a polynomial congruence mod p a prime, then there are at most n mutually incongruent solutions where n is the degree of the polynomial. Well, now we consider polynomial congruences where the modulus is composite. So we can actually use the Chinese remainder theorem to prove the following theorem about polynomial congruences with composite moduli. So let f be a polynomial with integer coefficients and let m be the product of m1, m2 up to m sub s, where the m's are pairwise relatively prime positive integers. m1, m2 up to ms are pairwise relatively prime positive integers. Then this theorem states that the congruence f of x congruent to 0 mod m has a solution if and only if each of the congruences f of x congruent to 0 mod mi for I equal to 1, 2, up to s, if each of these congruences has a solution. So we can check a polynomial congruence mod m by first checking all the congruences f of x congruent to 0 mod mi, where mi is a factor of m. If any one of the congruences with a smaller modulus is not solvable, then the congruence mod m is not solvable. Let's begin the proof. Let's prove the forward implication first. So I'm going to assume that f of x congruent to 0 mod m has a solution. Suppose A is the solution to f of x congruent to 0 mod m. Then we know that f of a is congruent to 0 mod m. So if m divides f of a, then each of the little mi will also divide f of a. And thus, f of a will also have to be 0 mod mi for each I. Well, that's the same as saying that A is a solution to each of the congruences f of x congruent to 0 mod mi. So A is a solution to f of x congruent to 0 mod mi for each I. Now let's prove the reverse implication. So I'm going to assume that each of the congruences f of x congruent to 0 mod mi is solvable. So for each I can find a solution. Let's call it AI. Suppose AI is a solution to f of x congruent to 0 mod mi. Okay, so we have a total of S congruences, and we have a solution to each one of these S congruences. Well, by the Chinese remainder theorem, there exists an integer a such that a is congruent to ai mod mi for each I. So recall that all the mi's are pairwise relatively prime, and so if we set up a bunch of linear congruences, x congruent to a1, x congruent to a2, and so on, then by the Chinese remainder theorem we can find a solution to that system. So a is the solution to that system. So a is congruent to ai mod mi for each I. Then when I plug in a into the function f, and I'm reducing mod mi, I can replace a with its residue ai. So f of a is going to be congruent to f of ai when I'm working mod mi, but ai is a solution to the congruence f of x congruent to 0 mod mi, so this will be congruent to 0 mod mi. And this works for each congruence for each I. So we see that A is a solution to the congruence f of x congruent to 0 mod mi, but since all the moduli are pairwise relatively prime, we also have that f of A must also be congruent to 0 mod m. So if all the mi's divides fa and all the mi's are pairwise relatively prime, then the product of them, which is m, must also divide f of A. So f of A is congruent to 0 mod m. Thus, A is a solution to the congruence f of x congruent to 0 mod m as required. So this finishes the theorem. So let's look back at the theorem. So this tells us if we want to solve a polynomial congruence mod m, we can actually solve congruences mod a smaller modulus where all the smaller moduli divide m. So let's see an example of this theorem. Suppose I wanted to solve the congruence x squared plus x congruent to 0 mod 35. So we see that 35 is 5 times 7, so I'm going to solve these congruences mod 5 and mod 7 first. X squared plus x congruent to 0 mod 5 and mod 7. Again, because 35 is 5 times 7. So the congruence mod 35 will only have solutions if the congruences mod 5 and mod 7 are both solvable. Well, we can factor this polynomial. This is x times x plus 1 and if x times x plus 1 is congruent to 0 mod 5, then we know that x is going to be congruent to 0 mod 5, or x is going to be congruent to, if I set x plus 1 congruent to 0, x will be congruent to negative 1 mod 5. And if we look at this congruence on the right, x times x plus 1 will be congruent to 0 mod 7, and x will be congruent to 0 mod 7, or x will be congruent to negative 1 mod 7. We have to combine these two congruences, mod 5 and mod 7, to get our solution, mod 35. So think about it. X can be 0 mod 5 or negative 1 mod 5, and x has to be 0 mod 7 or negative 1 mod 7. So we've got to combine a solution to the congruence mod 5 with a solution to the congruence mod 7 to get our solution mod 35. Well, you could do this by thinking about numbers that are 0 mod 5 and numbers that are 0 mod 7, for example. So you see, if I combined the solutions x is 0 mod 5 with the solution x is 0 mod 7, then x will have to be 0 mod 35. So we're going to get four distinct solutions here. So if x is congruent to 0 mod 5 is a multiple of 5, and 0 mod 7 is a multiple of 7, then x could be congruent to 0 mod 35. Now think about 0 mod 5 and negative 1 mod 7. So what residue mod 35 is a multiple of 5 and 1 less than a multiple of 7? Well, I see that the number 20 is 0 mod 5 and 1 less than a multiple of 7, so 20 would be congruent to negative 1 mod 7. Now let's find a residue that's 0 mod 7 and negative 1 mod 5. So multiples of 7 that are 1 less than a multiple of 5. Well, I see that 14 would be 0 mod 7 and 1 less than a multiple of 5, which is 15. So if I combine these two congruences, mod 5 and mod 7, I see that x would be congruent to 0 mod 35. And then finally, if I look at x congruent to negative 1 mod 5 and x congruent to negative 1 mod 7, then a number that is negative 1 mod 5 and negative 1 mod 7 would also be negative 1 mod 35. So I'm going to write that as 34. 34 or negative 1 mod 35, we see that it's 1 less than a multiple of 5 and 1 less than a multiple of 7. So these are four distinct mutually incongruent solutions to the original congruent, x squared plus x is congruent to 0 mod 35. Now there's another way you could solve this. If you want to, you could list out all of the residues that are 0 mod 5 in a complete residue class mod 35. So alternately, just since 35 isn't that big, let's look at residues that are 0 mod 5. There's 0, 5, 10, 15, 20, 25, and 30. Now I'm going to list out residues that are congruent to negative 1 mod 5. So we see that 4, 9, 14, 19, 24, 29, and 34 will be residues congruent to negative 1 mod 5. And then let's write out the residues mod 7 now. So x would be congruent to 0 mod 7. So there's 0 and then 7, 14, 21, and 28. These are all the residues that are congruent to 0 mod 7 between 0 and 34. And then do the same thing with residues negative 1 mod 7. It's going to be 6, 13, 20, 27, and 34. So remember, we have to combine a solution mod 5 with a solution mod 7. So x has to be congruent to 0 or negative 1 mod 5, and x has to be congruent to 0 or negative 1 mod 7. So look for residues that are on the list of residues mod 5 and also on the list of residues mod 7. We see that 0 and negative 1 or 34 are both solutions. So you can write 0 and negative 1 or 0 and 34. Let's look at other residues that are on both lists. We see that 20 is a residue that's 0 mod 5 and also negative 1 mod 7. And then the last one we see is 14. 14 is negative 1 mod 5 and 0 mod 17. So we get the same solutions. And so if you just list out all of the residues, mod 5 and mod 7, that are possible solutions, you have to look for solutions that are on the list for mod 5 and mod 7. Let's look at another example. Let's solve the congruence x squared plus 3x plus 1 congruent to 0 mod 22. So we see that since 22 is 2 times 11, if we look at this congruence mod 2 and mod 11, as long as those congruences have solutions, then there will be a solution to this original congruence. But notice that the congruence x squared plus 3x plus 1 congruent to 0 mod 2, this will have no solutions. Why? Well, if you look at the left-hand side, if you plug in any integer, the left-hand side will always be odd. Because suppose x was even, then x squared would be even, 3 times x would be even, x squared plus 3x would be even, but then when I add 1, that would be odd. Now if x was odd, then x squared would be odd, 3 times x would be odd, but x squared odd plus 3x, which is odd, when you add them together, you get an even number. When I add 1, it would be odd. So the left-hand side is always congruent to 1 mod 2, and so this will never be congruent to 0 mod 2. So since this congruence has no solutions, we can conclude that x squared plus 3x plus 1 congruent to 0 does not have any solutions either.